Hi, hello everyone. Welcome to lesson 2.5. We're going to be talking about higher order derivatives and graphs of derivatives a little bit today, okay? To go ahead and get started, please go ahead and do the do now that you see there, and then we'll check our work, okay? So the do now includes this first question, and then the three that follow it, all right? Go ahead and give those a shot. Pause the video, and then we'll check our work. All right, here we go. So we're going to check the equation of the tangent normal line. Well, to be able to write the equation of a tangent and normal line, we need a few things. We need the slope, which we now know comes from our derivative, and we need the point that those tangent normal lines are going to pass through. So our slope, we need to do our derivative work. So our slope f prime of x. We have what looks like a quotient here. So the quotient rule says low function times the derivative of the high function. So that'd be 6x plus 2. Low d high minus the high function, keep it all together the same, times the derivative of the low function, which is just 1, so I'm going to leave it like that. Notice I grouped everything in parentheses just to keep things nice and clean, over the low function squared, so that's x plus 2 squared. I need the derivative at 1, so f prime of 1. I'm going to plug 1 into all of this stuff now, so that'll end up being 3 times the quantity 8 minus, when I plug in 1 over here, I'll get 3 plus 2, which is 5, over when I plug in the denominator down here, 1 into it, I get 1 plus 2, that's 3 squared, which is 9. Will give me a total of, that'll be 3 times 8 is 24, minus 5 is 19 over 9. All right, so I now know my slope at x equals 1, which is 19 ninths. All right, let me just do a quick check, make sure that I didn't accidentally make a mistake in there. Alrighty, looks pretty good. Okay, cool. So there's our slope. That's the slope of our tangent line at x equals 1. But we need to write the equation tangent and normal line. So that also means we need the point. So let's go ahead and plug 1 into our function. We need to find f of 1. F of 1, if I plug it into my function, will give me 5 up top over 3 underneath. So I can write my tangent line and now have my point. The point I passed is actually 1 comma 5 thirds. And so my tangent line is y minus y1 is equal to the slope, which was 19 ninths, times x minus my x value there. There's my tangent line and my normal line. My normal line, I'll put it over here so I'm running out of space, is the same y minus 5 thirds, but opposite reciprocal slope, there we go, times x minus x1. Cool, there we go, there's our tangent normal line to that curve, to that curve, and x equals 1. We got some derivatives we want to find down here, so dy dx, always assess first what kind of function are we looking at. In this case, we have a product. We got two things multiplied together. So we need the product rule. Product rule says keep the first times the derivative of the second. The derivative, I'm going to put this in brackets, the derivative cosecant is negative cosecant of x, cotangent of x. There we go. We kept that first or initial function and then multiplied by the derivative of the second one. And then product plus, the product rule means keep the first derivative of the second, plus, then we take the derivative of the first, derivative of sine is cosine, times we keep the second function. All right, we can maybe do some cleaning up and things like that, but we'll just leave it like this for now. We don't have to do any simplifying. Some things can, but that's good enough. All right, our number 2 here, looks like we got a quotient. We got to do our quotient rule. So this dy dx. I'll keep the low function times the derivative of the high. The derivative of cosine is negative sine. Notice I put parentheses there. Low derivative of the high minus the high function, which is cosine of x, times the derivative of the low. The derivative of 2 to the x is the natural log of 2 times 2 to the x, all over that low function, 2 to the x squared. There we go. All right. Now we want to prove in number 3 here that the derivative of tangent of x is secant squared of x by applying the quotient rule. Okay, well, tangent, I'll do this in different colors so we don't accidentally get confused. Let's change that to blue maybe. Tangent. If I want the derivative of tangent, the derivative of tangent. Tangent is sine of x over cosine of x. So there's where my quotient is going to come from. My quotient is sine divided by cosine. So I do low function times the derivative of the high, derivative of sine is cosine of x, minus, then I do high, which is sine of x, times the derivative of the low function. So the derivative of cosine is negative sine of x. A little cramped there. Here we go. Negative sine of x. So, oh, I'm seeing some pattern here. All over the low function, which is cosine squared of x. Now we got to clean this up. So what do we get? We would get here cosine times cosine. That'll give me cosine squared of x. Negative sine times negative sine will give me plus sine squared of x, all over cosine squared of x. All right. Cosine squared plus sine squared. Hey, there's a Pythagorean identity. That is just 1 over cosine squared of x. 1 over cosine, that's the same thing as secant. This is 1 over cosine squared, so this is going to be secant squared of x. And there we go. That proved using the quotient rule that the derivative of tangent of x is secant squared of x. Cool. As a start here, I also want to just kind of show one more thing, and this goes to, I believe Kai asked it actually. How do we know, how can we prove what each of the derivative rules actually is? And the answer I gave was we can actually do it using our limit definition. So I actually want to prove that the derivative of sine of x equals cosine of x using the limit definition of the derivative. This is going to be real quick. Not that you have to know how to do this, but it's a good demonstration that this stuff works. I want to use the limit definition that says this. The limit as h approaches 0 of f of x plus h minus f of x all over h. That's what I'm going to use. And the function I'm going to take a derivative of is sine of x. So this is going to lead me to this. And just copy these steps down just to show that this actually does work. Limit as h approaches 0, f of x, in my case, the thing I'm taking a derivative of is sine of x. So this is going to be sine of x plus h. Again, f of x plus h is on the inside, so sine of x plus h minus sine of x all over h. Now this is where we need some of our trig identities. And you might remember that the sine of a plus b is equal to the sine of a times the cosine of b plus the sine of b times the cosine of a. If we use that identity, and in this case a is going to be x and b is going to be h, we can actually do something interesting here. The limit as h approaches 0 of sine of x times the cosine of h, I'm just using this pattern up here, plus the sine of h times the cosine of x. That just broke up the sine of x plus h, but there's also minus sine in there, so minus sine of x all over h. All right, this got a little bit uglier, but this will ultimately be useful for us because I'm noticing some things here, all right, that we can do. So if we're clever here, we can actually manipulate this using some algebra and get it down to something that's actually fairly usable and reducible for us. All right. If we want to prove this, sort of our next step, we got to think, okay, well, what can we do here? We're going to clump some stuff together then. I see that there's in here some sine of x stuff. So let me actually move the sine of x stuff closer together. Here's what I mean. So I'm going to take sine of x cosine of h. I'm going to move that minus sine of x a little closer, minus sine of x. And then I'm going to push that plus sine of h cosine of x a little farther away, all over h. I'm now going to factor out that sine of x. So that'll leave me the limit as h approaches 0 of sine of x. I'm going to factor out each of these sines of x just from these first two terms. So times the cosine of h. Oop, made a mistake there. Back up for a second. Times the cosine of h minus 1. So if I factor sine of x out, I get cosine of h. If I factor sine of x out of here, I get a minus 1. But then that plus sine of h cosine of x is still there. Plus sine of h cosine of x is still hanging out over there, all over h. Now we go, well, why is this useful? What can we do with this? Well, all right, if we keep working this thing down, the limit as h approaches 0 of this thing. Let's break this fraction up actually into two different things. We'll call it the limit as h approaches 0 of sine of x times the quantity cosine of h minus 1 over h plus sine of h cosine of x all over h. And we actually notice some things here. Notice that our limit is talking about h approaches 0. And notice here I have sine of h over h. That's interesting because we know that the limit as h approaches 0 sine of h over h is actually going to give us 1. So we can actually more or less forget about those things there, right? And if we think about, okay, well, what's going on over here, right? We have what's left over here, the sine of x times the cosine of h minus 1. This limit over here, let's figure out what's going to happen with it, okay? Because we already kind of figured out what's going on over here. This first limit then, the limit as h approaches 0, we can kind of ignore the sine of x part of this, right? But the cosine of h minus 1 over h, we still got to take care of. Well, if we try to plug in 0 in here now, right, if we try to plug in 0 in here now, we would get 1 minus 1, so that'll be 0 over 0. All right. This is where we have to kind of skip something here just in terms of the space we have. This limit, if you actually graphic or plug in numerical stuff, you'll find that the limit here is 0. We can also prove that using trig identities. So this limit here is also 0. Plus, we said the leftover thing over here is cosine of x. So if this limit is 0, it basically will kill that whole thing there, leaving us with just cosine of x left. The only thing I can't show here is that the limit as h approaches 0 of cosine of h minus 1 over h is 0. You can graph that and see it. You can also do it numerically, or using trig identities we can prove that. But because it's 0, it'll destroy the sine of x that's left over, and we have cosine of x left. So all of these derivative rules are actually provable along the way using algebra and graphical skills. Our main focus for today is actually just to introduce you to a new idea that's relatively short, and that's the idea of higher order derivatives. All right, given function f of x, what does f prime of x tell us? Well, we already said that f prime of x tells us the slope, if you will, of f of x at any x value. Right? We plug in an x value to f prime and tells us the slope of f at that x value. What if we want to know the slope of f prime of x? Well, in that case, we would need to calculate what we call f double prime of x. It would tell us the slope of the slope graph. If we kind of want to think about it that way. When we calculate derivatives past the first one, we call these things higher order derivatives. And they're actually really useful, higher order derivatives. Turns out that the rate of change of the rate of change, because remember a derivative is the instantaneous rate of change. If we find its instantaneous rate of change, that tells us something really useful. And if we find the instantaneous rate of change of that, it tells us something really useful. So these higher order derivatives get used a lot. All right. For each of the problem, let's find the indicated derivative. And there's a few notations that get used. We see this notation for the second derivative. Ooh, that should be a squared. This means the second derivative of y with respect to x, and we've done it with respect to x twice, so that's why the 2 is out over there. Or the other notation we'll see is f double prime like that. All right, so I'm going to do the first one, then we'll have you do the other ones. Let's find the indicated derivative for this problem. We want to find the second derivative of y, and we want to write out with the proper notation. So dy dx, the first derivative would be negative 2x, using the power rule. And then my second derivative The derivative of negative 2x would just be negative 2. Remember, the power rule says bring down the 1 that's on the exponent multiplied by negative 2. We get negative 2. Subtract 1 from the exponent. That means x to the 0, so it goes away. The derivative of a linear function is just the slope that's left. So there's the second derivative. All we did was just do our derivative rules twice to get down to the level that we wanted. Go ahead and try 2, 3, and 4, please. Pause the video and try that. All right. So f prime of x, not too bad. That's a power rule thing. We bring down the 3. That'll be 12x squared. The second derivative of x just means do it again. So we bring down the 2. That'll give us 24x. All right. dy dx, our first derivative of negative 4x will be negative 4. Our second derivative, the derivative of negative 4, that's a constant. The derivative of a constant is 0. And then the third derivative is taking the derivative of 0. Wait, the 0 is also a constant, so our derivative just stays 0. All right, our third derivative over here, f prime of x, is going to be 20x cubed. F double prime of x means take the derivative again. We got power rules going again, so we get 3 times 20, which will give us 60x squared. All right, 60x squared, and then our third derivative of x is going to be 120x. These multiple derivatives become really useful when we get to our last unit where we're going to be talking about Taylor series. All right. Cool, here's what I want you to try now. Again, we're just repeatedly using our derivative rules to get down to the level of the derivative we want. Go ahead and try 5, 6, and 7, please. Pause the video and try that. All right, we want the first 4 derivatives of y. So we have dy dx. The first derivative of sine is going to be cosine of x. Then we take the second derivative. That'll be this. The derivative of cosine is negative sine of x. Take the derivative again. Derivative of negative sine. So the negative will stay, the derivative of sine is cosine. And then we need to take the derivative of negative cosine. So the derivative of negative cosine, the negative will stay, but the derivative of cosine is negative sine. So negative sine will give us back to positive sine. We actually cycle back around to where we started, y equals sine of x. And we want to calculate the second derivative for this function, but we got to be careful. This is a product rule. So dy dx, the product rule says keep the first times the derivative of cosine. It's going to be negative sine of x. Plus, so keep the first, derivative of the second, plus derivative of the first, that's derivative of sine is cosine, keep the second. Now later on we're going to learn some other ways we can do this, but for now all we know are these rules, so we're going to go ahead and find the second derivative. But notice here we have 2 products, so we're going to actually have to do the product rule twice. Product rule for this and product rule for this. Later on we'll learn another way we can do this. All right, product rule for the first one says keep the second times the derivative, keep the first times the derivative of the second. Derivative of negative sine is negative cosine of x. Plus, then we take the derivative of the first. Derivative of sine is cosine of x. Keep the second. Plus, and now we can move over to our other term from our first derivative. Now we move over to this one. It's another product, so we use our product rule again. Keep the first times the derivative of the second. Derivative of cosine is negative sine of x. Plus, then we take the derivative of the first. Derivative of cosine is negative sine of x. Keep in mind my parentheses there. So I took the derivative of the first now, and we keep the second. In other words, I basically repeat the product rule twice. One for the first chunk, that ends up with these 2, and then one for the second chunk, and that's what ends up with these 2. And we could clean that up and stuff if we wanted to. Okay, we want to calculate the third derivative of this thing here. I see I have 1 over x. Let me just go ahead and rewrite this so I can see powers and stuff. Okay, so 1 over x is x to the negative first power plus cosine of x plus 1/3 x cubed. Okay, let me go ahead and do my first derivative. My first derivative is going to give me the derivative of x to the negative 1 is negative x to the negative 2. Derivative of cosine is minus sine of x. Plus derivative of 1/3 x cubed. I bring down the 3, multiply by 1/3. They'll cancel out, and I'll be left with x squared. My second derivative. Ooh, that got a little ugly. My second derivative. Derivative of negative x to negative 2. I bring down the negative 2, multiply it by the negative that's in front. That's a negative 1, so it becomes positive 2x to the negative 3. Derivative of sine is negative cosine of x. Derivative of x squared is 2x. So then my third derivative. The derivative of 2x to the negative 3 is negative 6x to the negative 4. Derivative of negative cosine is going to be positive sine. And the derivative of 2x is 2. And there we go. There's my third derivative. So remember, y prime and dy dx both represent the derivative. Two ways to write the same thing. Y double prime and this thing, oh, I forgot a squared, are both ways to represent the second derivative. When we get really big, into really higher order derivatives, we stop using the prime notation here, and we end up saying things like f of, let's back up. When we use this notation, we know that we're talking about the fourth derivative of f. So we stop putting prime, so we do it like that when we talk about fourth, fifth, sixth, seventh. I just want to show one thing we didn't have time to cover in class, which is, so we're not going to actually have to be able to, evaluate limit definitions. At this point, we have our derivative rules. What you need to be able to do, though, is recognize when you see a limit definition of a derivative, which should be really clear, because you'll either see it like this with our a plus h form, or something with x or some variable minus a constant over x minus a constant. All right? You can evaluate these using the limit definition, but I want us to do this instead. These are derivatives, so they represent the derivative of a function at some input value. So this is what I want us to do. I want us to identify the function whose derivative is being evaluated. We'll call it f of x. Identify the input at which it is being evaluated. We'll call it a. And then we'll determine the derivative by bypassing the limit definition. This is what I mean. Let me do 27 as an example here. In 27 here, I recognize this as a limit definition, our a plus h limit definition. There's a plus h limit definition here. All right, so I go, okay, what function are we taking a derivative of? And if I compare it to my a plus h limit definition, my a plus h limit definition looks like this. So my function is going to live right there and have a plus h on the inside. So if I look over here, I have 2 times a plus h. I think of this as like my x value. 2 plus something cubed. So my function then is 2x cubed. And we can see that over here too, 2 something cubed. So what value am I taking the derivative at? Well, in that initial problem, it was 5 plus h. So my a value is 5. I can also see the 5 there. So I'm taking the derivative of 2x cubed, 2 something cubed, 2 something cubed, 2 something cubed, at 5. So I can do that by hand now. F prime of x, the derivative then is 6x squared. F prime of 5 then is 6 times 5 squared is 25, which will give me 150. So I didn't actually have to evaluate this using the limit definition of a derivative. I could just go ahead and figure out what function are we taking derivative of and at what point, and work it out using my derivative rules. We can also do 29 this way. It's the other definition of a derivative. Our other definition of derivative says the limit as x approaches a of f of x minus f of a over x minus a. So I say, okay, what function am I taking the derivative of? I always will see that first. So in this case, it looks like I'm taking the derivative of x squared. At what a value? The a value is nice. It'll be right there in this limit definition. So a is 2. So f prime of x is 2x. F prime of 2 then is 4. There is always, always, always a limit definition of a derivative question on the AP exam. Always. You don't have to do it using the limit definition. You can use your derivative rules, but there's always a question there. Go ahead and do, which one would be good? Go ahead and do, let's go ahead and do 31. Do 31 right now. Pause video, do 31, and then come back and check your work. All right, here we go. 31. Notice here, we kind of switch some things around. Our variable is actually t. So f of t is t squared. That's the function I'm taking a derivative of. What is my a value? Where am I taking the derivative? I'm taking the derivative at x. And so f prime of t is 2t. F prime of x then will be 2x. That is my derivative. It's a general derivative. And there we go. Cool. Just a thought here. If you want to come back and practice these and have me check them, let me know. Okay? Last thing for today. Let's sketch the graph of the derivative of the function that is shown here on the same axis. And let's see how they compare. All right. F of x is the graph we're looking at here. Now remember, f prime of x represents the slope. So the y values of the, if I graph the derivative, the y values of the derivative will actually tell me the slope of the original graph. So let's actually find the slopes of this graph. I'm just going to label them on here for a second. All right, the slope along this section of the graph, remember this is f of x we're looking at here. The slope along that first section of the graph looks like it's -1. The slope along this section looks like it's +1. Then the slope becomes -2. Again, I can count down 2 over 1, or I can use the slope formula. And then over here, it looks like our slope is +0.5. Up 1 over 2. So what do we do with that? If I want to graph the derivative then, at the x values of each of these sections, the y value of the derivative graph will tell me the slope. So if the slope along this section was -1, then it's just going to be a flat line at -1. Again, the y value of the derivative graph I'm going to put in red. The y value of the derivative graph tells me the slope of this original graph. The slope along here was all -1, so the derivative graph is just going to be a flat line at -1. The slope along here was +1. So it's going to be a flat line. My derivative graph is going to have a flat line at +1 for that whole interval that corresponds with it. The y value here tells me the slope of this section. Here the slope was -2. So the y value of my derivative graph is going to be down here at -2 for the whole interval there, where the blue graph has a slope of -2. Then the slope of this last interval is +0.5. So my derivative graph, my red graph, is going to have a slope, or have a y value up here at +0.5. All right, so that's what the derivative graph looks like in red. Notice there are certain places, these corners that I kind of skipped. You can't find a slope at a corner. It's like a hinge. There's no tangent line there. The tangent line would just wobble around, just like you can't, you kind of can't balance if you have like a pointy mountain. It's really hard to balance a single line on it because there's an infinite number of lines that will balance or that will fit and kind of wobble across those corners. So the graph here, this function, is actually not differentiable at x equals -3, x equals 0, and x equals +3. All right. Here's what I'd like you to do. I want you real quick to go ahead and repeat the steps we just did with the graphs below. There are 4 of them, and go ahead and label the derivative function. Go ahead and do that. 1, 2, 3, 4 graphs. Sketch the derivative graph on the same axis and label the derivative. All right, let's take a look. Here we go. For this first one, it looks like our slope here is all +1 for this whole section. So that means my derivative, starting at that edge, edges we're going to say are not differentiable for now. And the whole interval has a slope of +1, so this is just going to be a flat line in our derivative for that whole interval until there. We have a break, so we can't take a derivative at that break there. We can't find a single tangent line that'll fit. We'll get into more of that later. And then a slope down here of -1 for that interval. So our derivative graph has a y value of -1. It is not differentiable. I'm just going to use ND for that. Not differentiable at x equals 1. And I'm not going to worry about the boundaries of the domain here. We're going to worry about the internal not differentiable places. Not differentiable at 1 here. So here is our derivative. All right, for this one, it looks like we got a slope of +2. And so our y values for this interval will be +2. It's just a flat line there the whole time. There we go. And up here we have a flat line. So that'd be actually a slope of 0. So for that interval, our y values of our derivative are at 0, because the slope here is 0 all the way through. And then our slope changes down to a slope of -1. So then our derivative graph jumps down to be a flat line, -1 for that whole interval. All right, here is our derivative. And the internal non-differentiable spots, again, we're not worried about the edges right now. We'll get more into non-differentiability later. The internal spots where we have differentiability problems are at x equals -1 and +1. All right, another graph here. We got slope of this graph. The slope of this graph on that interval is -1. So our derivative graph, notice this one has arrows. So our derivative graph is just a set of y values at -1. We got a corner though, so I'm going to cut it off there. Then our slope becomes +1. So we're going to have a set of y values in our derivative that are just at +1. Again, the y values of the derivative measure the slope of the original graph. Y values at 1 mean the original graph has a slope of 1 that whole time. And our non-differentiable internal element here is at x equals -1. Here is our derivative. All right. Cool. This was actually supposed to have arrows. I apologize for that. Well, this one's interesting. We have a flat line here at whatever y value that is, maybe 1.5, but the slope is 0. So our derivative then has a set of y values at 0. The y values of the derivative measure the slope of the original graph. Then our slope becomes, looks like +½ up 1/2. So our derivative graph has a flat line at +½ Oop, got to keep going along that entire interval. And then we have a slope of, this one's a little more challenging, huh? Looks like we go down, it looks like it's about at -½ so -1.5, -2.5. So it looks like we go down 2 over 2. Oh, it looks like it's a slope of -1. All right, so it looks like -1. And so I'm going to have my derivative graph just have a flat line. Oh, I started at the wrong spot, didn't I? Have a flat line at a y value of -1 there, on and on and on. So there is my derivative graph. And my non-differentiable spots on the inside are at x equals -2 and x equals +1. All right. Cool. Here's what I'd like you to do. I'm going to turn some of the optional homework into actually required stuff. What I would like you to do is I want you to, at a minimum, for practice, do page 150. Numbers, that should be number 1 through 11 odd, 35, 37, and 59. Okay? You can do the other ones for optional homework to continue uploading those and to get credit for those. But at a minimum, you need to do those problems I just outlined right now. Okay? Starting on page 150, you will find them there. Okay? Oh, actually, yeah, you'll find them there. All right? I'll talk to you later. Bye.